An object suspended from a wheel. A thin light wire is wrapped around the rim of a wheel, as we can see in the figure. The wheel rotates without friction about a stationary horizontal axis that passes through the center of the wheel. So it passes through this center. So it's in the z direction. The wheel is a uniform disc with radius 0.28 meters. An object of mass 4.2 kilograms, this object, is suspended from the free end of the wire. The system is released from rest and the suspended object descends with constant acceleration. If the suspended object moves downward a distance of 3 meters in 2 seconds, what is the mass of the wheel? Well, we have a displacement on the y-axis. Delta y is minus 3 meters in j-hat direction. And this happens in a time interval of 2 seconds. And since we have constant acceleration motion, we can call this constant acceleration A. This displacement magnitude will be equal to 1/2 a delta t square. So 1/2 a t square is equal to delta y. So this is going to give us an acceleration minus 3 is equal to 1/2 a delta t square. So acceleration we find is minus 1.5 meters per second square in j-hat direction. So it is in minus j-hat direction actually, because it's accelerating downward. Now if we draw the free body diagram of this block, the 4.2 kilogram block, we observe two forces acting on it, the weight and the tension in the cord. So modeling it as a point particle, we see the weight and the tension. Tension T pointing up, the weight pointing down, and this is our y-axis. The net force on the y-axis is responsible for the acceleration on the y-axis. ma equals minus 1.5 m. Tension in j-hat direction, mg in minus j-hat direction. So this is basically going to give us T minus mg equals ma. T is equal to m g minus a, or it is 4.2 times 9.8 minus 1.5. So this gives us a tension of 34.86 newtons, which is roughly 34.9 newtons. Now if we concentrate on the wheel, for the wheel we have the tension acting on it in the tangential direction. So this is the tension T, and if I draw the r vector from the pivot point, I can see that there will be a net torque acting on it. Net torque is equal to I alpha. So if I use the torque approach to solve this problem, this is basically what I'm going to concentrate on. This torque comes from R cross F, which is capital R T. Now using the right hand rule, R cross F is in minus k hat direction. So this is in minus k hat direction. In other words, this minus k hat implies that there will be a sense of rotation in the clockwise direction. So this will be accelerating in the clockwise direction. So minus sign indicates clockwise sense of rotation. Okay, and how much is this torque? It is equal to 0.28 times 34.86, because the angle between them is 90 degrees. I will get sine 90 equals 1 in minus k hat direction. So the torque turns out to be 9.7608 Newton meters in minus k hat direction, or roughly speaking, it is 9.76 Newton meters in minus k hat direction, up to 3 significant figures. At the same time, I have a tangential acceleration here due to this rotation motion. The tangential acceleration is related to the rotation. A is equal to angular acceleration times r. So we can write angular acceleration is a divided by r. Now this is a uniform disk. So what is the moment of inertia of a uniform disk? Let's calculate. I center of mass. The mass element dm, differential mass element that you can find in a uniform disk, is shown here. You can see that if I'm at a distance r from the center, I have an arc length r d theta and an incremental change in the radial position dr. dr times r d theta gives us roughly this area, which is the area of the differential element. So this is going to be sigma mass density times dA. If it is uniform, we have a uniform mass distribution. Total mass capital M divided by pi r square is the mass density, and r dr d theta is the area element. Then the center of mass, moment of inertia, will be integral r squared dm with respect to the center. This will be integral from 0 to 2 pi and radius from 0 to capital R, capital M over pi r square. R square times, so we have an r square and r dr d theta, we obtain r cube dr d theta. This gives us 2 pi times the integral of r to 3 dr will give us capital R to 4 over 4 when evaluated between 0 and r. So we will have r to 4 over 4. The angle does not appear anywhere here. So this integral of 0 to 2 pi d theta gives us delta theta, which is 2 pi. And then we have capital M divided by pi capital R square, which gives us capital M r squared over 2 as the moment of inertia of a uniform disk with total mass M, radius capital R. So with that, the torque equals I alpha equation gives us mr squared divided by 2 moment of inertia times alpha, which is a over r. This is equal to the torque, which is r times t. So this gives us, we have a simplification here. The r's disappear basically. So this r gets rid of this r, and then this r gets rid of this r. So we have, as a result, capital M is equal to 2t over a, which is 2 times 34.86 newtons divided by 1.5 meters per second square. That gives us 46.48 kilograms, which is roughly 46.5 kilograms. Okay, so we found the mass of the wheel. So that was the question, what is the mass of the wheel? So using this torque approach, we can easily find the mass of the wheel. Now, we can alternatively have an energy approach. So let's talk about an alternative approach here. Alternatively, we can use energy approach. Okay, so the final velocity, V final, will be equal to AT j hat, which is minus 1.5 t j hat, starting time from t is equal to 0. So this will be minus 1.5 times 2 j hat minus 3.00 meters per second j hat will be the final speed of the block. And the tangential speed is related to angular speed, omega final times r. So the angular speed will be equal to 3.00 divided by 0.28, which is roughly 10.7 radians per second final angular speed. And remember, the object starts from rest, so we're going to have initial kinetic energy 0 joules. Now I note that 1 over 2 mv final square will be the final kinetic energy, final translational kinetic energy of the block. And we have 1/2 I omega final square will be the final rotational kinetic energy of the wheel. And where does this energy come from? Well, we initially have a potential energy mgh, which is 4.2 times 9.8 times 3, 123.48 joules. And we have a final kinetic energy 1/2 mv final square plus 1/2. So this is with respect to center of mass. So I center of mass omega final squared, and final potential energy is 0 joules. That's how I define the potential energy scale. And there is no friction in the system, so this is rotating without friction. So we're neglecting all the friction here, and therefore we must have conservation of mechanical energy. Delta E mechanical is equal to 0 joules, which means the change in kinetic energy must be equal to minus the change in potential energy. So 1/2 mv final square omega final square r square plus 1/2 I center of mass m capital R squared over 2 omega final square is equal to the change in kinetic energy with a minus sign that gives us mgh. So we obtain this equation. If we multiply it by 4, we will obtain 2m omega final square r square plus capital M r square omega final square is equal to 4m gh. Now if we isolate capital M here, this will be 4m gh minus 2m omega final square r square divided by omega final square r square. So this will be 4mgh minus 2m v final square divided by v final square, or we can write capital M as 4mgh divided by V final square minus 2m. So this is equal to 4.2 kilograms, 9.8 meters per second square, 3 meters, divided by the final speed squared. So the final speed was 3, so it's 3 squared. Remember, it was minus 3 meters per second j hat. So this is 9 minus 2 times 4.2, and this indeed gives us 46.5 kilograms up to 3 significant figures. Okay, so we obtained the same result using two approaches, torque approach and energy approach. So we had this system initially at rest, and then this block starts accelerating downward with a constant acceleration so that it moves a distance of 3 meters in 2 seconds. So a displacement of minus 3 meters in 2 seconds corresponds to an acceleration 1/2 at squared delta y is equal to delta y minus 1.5 meters per second square. Notice that the acceleration of this block is the tangential acceleration of this wire. Now, that is wrapped around the wheel. So, if we draw the free body diagram of the block, we see two forces acting on it, the tension and the weight. So there is mg pointing down. So T minus mg is the net force in j hat direction. The net force in j hat direction is minus 1.5 m because the acceleration is negative. It's accelerating downward. So we can find the tension here. The wheel, on the other hand, feels a torque due to this tension. The net torque acting on it using R cross F is the radius multiplied by the tension, with giving a rotation with clockwise sense of rotation, and tangential acceleration is related to angular acceleration. A is equal to alpha r, so alpha is A over r. Then we can calculate the moment of inertia with respect to the center of mass, a rotation axis that goes through the center of mass of this wheel. And this is a simple calculation. If you concentrate on a disk, uniform disk here, you can see that the area element is r dr d theta. R d theta, the arc length, dr is the differential distance in the radial direction. The mass density is capital M divided by pi r squared. Capital M is the total mass of the disk. Integrating this for all possible angles, 0 to 2 pi, for all possible radial distances from 0 to capital R, we obtain mr squared over 2. Substituting this result into the torque equals I alpha equation, Newton's second law rotational form, we obtain R times T, the magnitude of the torque, is equal to I times alpha, the magnitude of I times the magnitude of alpha, which gives us a mass of 46.5 kilograms. Alternatively, using the energy approach, we have initial kinetic energy 0 joules, initial potential energy, we are at a distance of 3 meters from the ground, and as it falls 3 meters, this is going to gain a kinetic energy, translational kinetic energy, and because this wheel will be rotating, it will gain a rotational kinetic energy, so that we will have 1/2 I center of mass omega final square, final rotational kinetic energy, and 1/2 mv final square, final kinetic energy of the block, which comes from the loss of potential energy, mgh. Final potential energy is 0. So if we substitute for I center of mass mr squared over capital mr squared over 2 and solve for capital M from this equation, we obtain exactly the same result, 46.5 kilograms.